So how do I go about graphing this rather simple looking function? It's f of x equals cos squared 2x, which actually means cos of 2x all squared, if you remember. So this question came from the textbook, and in the textbook it asked you to consider extrema and concave up and concave down and inflection points, all that kind of stuff. And it is true that you could do all of this as pure algebraic calculations and then take your calculations and draw the graph. But I'm going to do something slightly different, but I'll come back to the algebraic calculations towards the end. And what I'm going to do is I'm just going to take what I know about cosine functions and start there at least. And the idea, this is my thought bubble, is that by considering what's going on, first of all, it might just give you an idea about the shape. Now, we know cosine graph is kind of that kind of graph. It's a sinusoidal wave, but starts off with the maximum, I suppose. So that's something. And then you can think, well, what's the effect of the 2x? Well, we know that it's just going to go through its periodic motion faster. Then we've got this square. What's the effect of the square? Well, I know that for cosine graphs and sine graphs, usually they go between -1 and 1, but all of these minus values are going to be squared, which means that we're going to be lifted up here. And then when you square a fraction, you get a smaller fraction. So when I square 1, I'm going to get 1. When I square -1, I'm going to get 1. And then every value in between, and when I square 0, I'm going to get 0. And every value in between is going to be squished down. Now, I don't know what that will mean in terms of the final graph, but at least I get a sense that it's going to be a cosine graph that's not going to dip below the x-axis because all the values are going to be squared. So it gives me a sense. That's all. Okay, let's use a little bit of derivative work, though. So let's go with f dash of x to start with, because this will give me my extrema. So I will find the derivative of cos of 2x all squared. I'm going to use the chain rule for that, so it's a double chain rule. So the inside function is 2x, and the derivative of 2x is 2. And then the derivative of cos with respect to 2x is negative sine. So I'm going to multiply that by negative sine of 2x. And then the derivative of square is 2 multiplied by whatever's inside the square. So I've got multiplied by 2 cos 2x and subtract 1 from the power. So that's the full derivative there. And I can sort of reorganize that to be negative 4 sine 2x cosine 2x. Okay, that's all right. And if you think about it, this is sine of an angle multiplied by the cosine of the same angle. 2x is just the same angle as here as it is here. And this -4 can be split up a little bit to -2 times 2. So we've got -2 multiplied by 2 sine cos. So we've got the double angle rule. I'll spell it out for you so you can sort of see it. And so because we've got 2 sine A cos A, we know that means that's sine 2A. So we have to double that angle there. So again, I'll spell it out, but that's -2 sine of 2 times 2x. It's a double angle rule. So that gives me -2 sine 4x as being the derivative. Okay, so I'll just keep it zoomed out so we can see it all. So what does that mean? We know that there are minimum and maximum values at the derivative equal to 0. Just because it's a trigonometric function doesn't change that basic fact about derivatives. The turning points are found at f dash of x equals 0. These are relative minimums and maximums, of course. So I set the derivative equal to 0, which gives me, if I divide both sides by -2, sine of 4x equal to 0. And then just to save time, I'll just do the substitution. But instead of going from 0 to pi, as I didn't write that down, but it was in the question. Sorry, I'll just put it in a different color so you can see it. It was meant to be 0 between x between 0 and pi. So we're looking for theta between 0 and 4 pi, okay? Because we've just done that quick substitution so we can make more sense of it. So what does that mean? Well, when is sine theta equal to 0? Well, that'll be theta is equal to, well, just as a little unit circle here, the sine of an angle being equal to 0 occurs either here or here in the unit circle. So it'll be when theta is equal to 0, or theta equal to pi, or theta equal to 2 pi, or theta equal to 3 pi, or theta equal to 4 pi. So again, 0, pi, 2 pi, 3 pi, 4 pi. All of those are possible solutions, really, for theta. And that's what 4x equals. So therefore, x equals a quarter of all those sorts of things. So we've got x equals 0. Sorry. X equals 0, because 0 divided by 4 is 0. Or pi on 4. Or 2 pi on 4, which is pi on 2. Or 3 pi on 4. Or 4 pi on 4, which is just pi. So all of those are going to be min or max values. So that's fine. And we might note that 0 and pi are also the endpoints, because if we're going to graph between 0 and pi, we need to know the endpoints. If they weren't included in this list, then we'd have to do them separately, but they are, so we're all good to go. What we'll do now is we will take each of those values and we'll simply work out the y coordinate by substituting each of those values into the original function. So we're going to look at f of 0 first. And that's going to be equal to the cosine squared of 2 multiplied by 2 multiplied by 0. So that's just 0. The cosine of 0 is 1. Again, if you have a look at this little quadrant thing here, the cosine of 0 is when is all the way out here. So it's 1 unit away from the x-axis. So the cosine of 0 is equal to 1. Square 1 and we get 1. And so we have the coordinates 0, 1. If I now do the same thing with the next one along, so that's pi on 4. So f of pi on 4 is equal to the cosine squared of, now 2 times pi on 4 is pi on 2, right? So I'm just left with pi on 2 in here. The cosine of pi on 2, again, looking at the quadrants here, pi on 2, the angle is up here. There's no movement in the x direction. So the cosine of pi on 2 is just 0. And 0 squared is 0. So that means we've got another point, which is that at pi on 4, the coordinate is 0. F of pi on 2 is equal to the cosine squared of, so 2 times pi on 2 is just pi, and the cosine of pi is -1. Okay, so that's over here, -1. but -1 squared is +1, and so we get 1, which is equal to, so therefore the coordinates are pi on 2 and 1. And I'll just squish the other two down here. 3, 1, 2, 3, 4, 5, get the other two down here. So we've got f of 3 pi on 4 is equal to the cosine squared of, so 3 pi on 4 multiplied by 2 is 3 pi on 2, and 3 pi on 2 is down here where the cosine of, where cosine is 0, and so we get that equal to 0. So that means 3 pi on 4 has a y-coordinate of 0. And we've then got the last one, which is f of pi, which would equal the square of the cosine of 2 times pi, which is 2 pi. And the cosine of 2 pi is equal to 1. Again, unit circle. Let's have a look at it. 2 pi is all the way around, and it's back to 1 again. And so we have a coordinate of, no, not 2 pi, sorry, but pi, comma, 1. So I'll just highlight those so that we can see it a little bit more clearly, perhaps. Just choosing a highlight color. That one will do. So we've got that one, that one, that one, that one, and that one. Okay, so they're our 5 coordinates that we've got. Now, the next thing we can do is start graphing straight from there, believe it or not. So I'll do that in slide 3. So we can see from our extrema there that we're going to go from as low as 0 and up to 1, and we're not doing anything below the x-axis there. So I'll just draw the y-axis and the x-axis like so. And we can see that we're going to go from 0 to pi, and I'll split that in 2, so that's about pi on 2 there, and I'll split it in 2 again and go pi on 4 and 3 pi on 4, like so. And then we can sort of start seeing some of those coordinates. So if I just call that 1 there, or maybe that's a bit too high for what I'd like to do. Let me just have it there instead. Okay, so just with x's, I'm going to put in each of those points. So the first extrema is 0, 1, so that's there. And then I've got pi on 4, 0, and that's there. And then I've got pi on 2, 1, so we're back up to the top here. And then we've got 3 pi on 4, 0, and that would be back there. And then pi and 1 would be back up there. So there's our coordinates there. And then we know what shape we're looking for. And we know that for a cosine graph, well, I hope we know this, that a cosine graph changes concavity halfway between the maximum and the minimum. In other words, I'll do it properly in a second, but it'll go from being that shape to that shape halfway between the maximum and the minimum. So I'll just put those in here. Well, halfway between 0 and pi on 4 is going to be pi on 8, right? And then halfway between these two is going to be 3 pi on 8. So we've sort of got 1 pi on 8, 2 pi on 8, 3 pi on 8. Then we've got 4 pi on 8, or pi on 2. And then we've got 5 pi on 8. And then we've got 7 pi on 8. And this is halfway between 1 and 0. And so that would be at a half, or 0.5. And so that these red dots here are going to be our changes in concavity. Again, nothing calculated here, just what I know about how cosine works. So I might just draw it in blue, but what I'll do now is I'll just draw the first part of the curve here, and then I'll draw the next part of the curve here, and then I'll draw the next part of the curve here. That was a bit dodgy. I'll just try that one again. Oops, changed color as well. That was interesting. Next part of the curve here, and then the next one is here, and then the next one is here, the next one is here, next one is here, and the last one is there. Now, I've done that really roughly and really quickly, but you get a sense of the drawing there. So that's fine. I've now got a graph. I've now got a I've now worked out the extrema, and I'm kind of ready to go. The question was, tell me about where it's increasing and decreasing, etc. So we can just sort of answer those now that we've got the graph without doing any calculations. So where is the graph decreasing? So decreasing, remember, means that the graph is going down. So let's write them as intervals. So just be mindful, I'm going to use interval notation, which looks like coordinates, but it's not, because we're talking about a range or domain of values. So it's decreasing from 0 to pi on 4. Again, that's not a coordinate, that's a set. So again, from here, where x equals 0, to here, we have it decreasing. Might make more sense, perhaps, if I put the x as an element of before it, maybe, if that helps. X is a member of 0 to pi on 4, it's decreasing. Where else is it decreasing? So it decreases there, and then it decreases there. What's that? That's pi on 2 to 3 pi on 4. So let's put that down as well. Pi on 2 to 3 pi on 4. So that's the decreasing parts of it. Where is it increasing? Okay, so it's increasing. It's going up from pi on 4 up to pi on 2. So I can write that down. Pi on 4 up to pi on 2. Again, remember, these are not coordinates. These are sets, set notation. They're not increasing at those endpoints because they're turning points, but they are increasing up to those endpoints. And then the last one is it's increasing from 3 pi on 4 up to pi. So I can go 3 pi on 4 and pi, like so. So that's where it's decreasing and increasing. We were also asked about inflection points. And as I said to you before, the inflections are halfway between. So we can simply write the inflections. We can write the inflections at, well, we know there's one inflection at pi on 8, and it's just a half, or 0.5, right? Every single time it's going to be a half. So I can write pi on 8, 3 pi on 8 and a half, 5 pi on 8 and a half, and 7 pi on 8 and a half. These are coordinates this time. These are coordinates. Before they were ranges or domains, sets. These are now coordinates. So how do you know whether it's a set or whether it's a coordinate? It's context, right? So inflections are points, but areas of decrease and increase are sets. Okay, concave down. Try not to get my picture this time. So concave down, looking at the picture. So concave down would be where it's kind of this shape. Yeah, so that's concave down. So it's concave down between here and here, down to the inflection point. So that would be between 0 and pi on 8. So again, these are now ranges, sets. Where else is it concave down? Well, it's concave down from here all the way down to here. That's concave down. So that's 3 pi on 8 to 5 pi on 8. And lastly, at the end there's a bit of concave down here. So it's from that inflection point where it stops being concave up and starts being concave down again. We've got 7 pi on 8 and pi as being the domain there. Okay, and concave up, guess what? It's the rest. Okay, I'll do these underneath that so I don't hit my graph. So concave up is going to be this bit here and this bit here. So concave up is, I can probably fit it next to it actually, is pi on 8, from pi on 8 to 3 pi on 8. And then it's also from 5 pi on 8 to 7 pi on 8. These are the two areas that it's concave up. So that actually answers all the question. It didn't touch second derivatives or anything else. The first derivative gave me the ability to work out the maxima and minima, but then that was all I needed really in order to draw the graph, because I knew what a cosine graph was going to end up looking like. So that's all well and good. But what happens if we need to confirm all of these calculations by algebraically? So I'll go to the next page and sort of show you how it all is confirmed. But that's basically it for if you need to find the graph from the function. Okay, so let's have a look at this. And let's start off with the inflection points, first of all. So we know that the inflection points are at f double dash, second derivative, equal to 0. So just so we don't have to flick between pages, f dash of x was negative 2 sine of 4x. And so the second derivative is found by differentiating the first derivative. So again, chain rule, the derivative of 4x is 4, so we'll have 4 times minus 2, which is negative 8, and the derivative of sine is positive cosine, so it's negative 8. Oops, sorry, negative 8 cosine of 4x. That's the second derivative there. So all we need to do is find out exactly when we set that equal to 0, what are the values of x, like so. So if negative 8 cos 4x is equal to 0, then that means the cosine of 4x is equal to 0. And that means that the cosine of theta is equal to 0, because x was between 0 and pi. X is now between 0 and 4 pi, beg your pardon. Should be theta there in the middle there. Okay, so that's okay. We can work that out. Very similar to what we did before, really, is when is cosine of theta equal to 0? We've got our unit circle here, and cosine of theta is equal to 0 here and here. And so that means that theta is equal to pi on 2. That would be this bit, and then another pi later. So 3 pi on 2. And then we'll go around again, and that would be 5 pi on 2. And then lastly, 7 pi on 2. And then that's what 4x is equal to. So we'll divide everything by 4, and we would get pi on 2 divided by 4, or pi on 4 times a quarter. So that would be pi on 8, 3 pi on 8, 5 pi on 8, and 7 pi on 8 as our x coordinate, which is what we've got here. Pi on 8, 3 pi on 8, 5 pi on 8, 7 pi on 8 is our x coordinates. So in order to work out the points, of course, we would substitute those in to the function, and we would get a half each time. For example, I'll just take the first one, pi on 8. We would have 2 times pi on 8, which would be pi on 4. Pi on 4 is 1 on root 2, or root 2 on 2, but 1 on root 2 is good for us to know because the square of 1 on root 2 would be 1 on 2, which is a half. And that would be the same thing for 3 pi on 8, 5 pi on 8, 7 pi on 8. It will give us the same sort of thing. It'd be 1 on root 2, then we would then square that to get a half. Okay, so I won't go through the actual coordinate finding there, but that's pretty much it. So the inflection point is when there's a change in concavity, and so you can use the fact that there's a change in concavity to figure stuff out from there. The other thing you could do is you could do a sine chart as well. So if we have a look at all the critical points, so we can look at, if I just go up in lots of pi on 8, so 2 pi on 8, which is pi on 4, right? 3 pi on 8, 4 pi on 8, 5 pi on 8, 6 pi on 8, 7 pi on 8, and 8 pi on 8, which is pi. So if we have a look at that, we know that for all these ones here, we've got 0, 3, 5, and 7. They're all zeros. That's the change in concavity. And then if you have a look at the other values, they're either maxima or minima. And so you can see that this is for f dash dash of x. So you would have, if you substitute these values in for f double dash of x, you'll see that that value is negative, and that value is positive. For f dash dash of x, that value is negative, that value is positive, and that value is negative. And so you can see that between 0 and pi on 8, we're going from, we've got a negative value for f of x. And because there's no turning point between them, it can only have one direction. It can either be concave up or concave down. And we know that for concave down, f double dash of x is negative, right? So that means between 0 and pi on 8, we've got concave down. So I'll just put concave down here. And between negative pi and 0 here, so we're between here and here, it's concave down, and that's and between here and here, it's concave down. And so for concave up, we're going to have between the zeros, there's a positive there, and between the zeros, it's positive there. So that gives us our concave ups. And so we would say between 0 and pi on 8, it's concave down. Between 4 pi on 8, which is pi on 2, and 5 pi on 8, it's concave down. And 7 pi on 8 and pi, it's concave down. And I think you'll find that's what we had here. And concave up, just those two intervals there and there. So that gives you a sense of the f double dash and its relationship there. So hopefully that makes sense to you, and it sort of goes some way of linking all of those sorts of values behind. So technically, again, just in terms of a sine diagram, I could have said there's a change of concavity here, 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 and here, and therefore it's gone from down to up, and then from here it's changed concavity, and there can't be another change of concavity in between because these inflection points exactly tell us that there's a change in concavity. So if there's a change in an inflection point here and an inflection point here, then everything in between must be concave up, and everything between here and here must be concave up as well. Okay, so hopefully that makes sense. The one thing I didn't go through, which I could have, but I could have looked at the turning point. So f dash of x equals 0. I could have written that as a sign diagram as well and looked at f dash dash of x. If we had done that, we would have found that at the turning points, some of them, the f dash dash of x would have been negative, which would mean that they are a maximum. A maximum because they're concave down at that point. And for the other turning points, they would have had f dash dash of x equaling a positive number, which means they're a minimum because they are concave up. So that's just, again, just another table of values that you can figure out from there. If you let me know, I can sort of go through a tutorial on that as well. But I'll leave it there for the time being. I'm hoping all of that sort of brings it all together. Yeah, I could have done all that algebra first and then drawn the graph last, but I think it's equally valid to do it this way. And then all of this stuff here is just confirmation that my drawing of my graph is correct. Okay, thanks for watching.